Okay, so like I said, you should have your surface looking in some condition of those, of just having 3 designated surface types. I'm going to start off with our forest uh, pieces. So the first thing I'm going to do is go to my parameters and reference those surfaces. So I'm going to drag this over here. I'm going to try my best to organize this so you can remember the names of everything. So I'll just right click this, change it from being surface to, I think it's referred to as forest or woods is the variable name or the coefficient name. So we'll call it woods. Now I'm going to select my wood surfaces. And I'm going to right click on woods and say set multiple surfaces. So pretty standard approach. We've done that quite a bit of just bringing a surface in. So the first thing we need to do is actually divide these surfaces, because we can see, even though I have this surface, for example, I can easily find its area, but I can see that there's quite a lot of variation to its overall area, right? There's extremely steep areas. There's a little bit of flat areas on the top. So it's not safe to say that we can just get an average slope percentage of this, right? There's all sorts of different variables. So what we need to do for all of these is actually kind of fragment it down to much smaller surfaces to find their average area and coefficient values. So the best way to do that is first convert it to a mesh. And we're going to do that by taking that surface. We're going to populate it with some points. So I'm going to go to vector, grid, populate, geometry. So we're going to create a series of random points on these. You can keep the default value of 100. It really doesn't make a whole lot of difference. Obviously, the more points you have, the more detail you're going to have. With these points now, we're going to use them to create a surface that's made up of a bunch of different fragments. So now I'm going to go over to mesh. I'm going to go over to triangulation. And I'm going to do Delaney edges. So again, mesh, triangulation, Delaney edges. Don't do Delaney mesh. We would just want the edges. So I'm going to plug that into there. You can turn those points off, and I'll see that I've got this kind of triangulated grid that's covering my surface. Now what we want to do is actually convert those edges into a surface. This is, I think, one of the easiest ways to fragment these surfaces into smaller surfaces. There's a couple other ways, but for this, probably the most effective. So I have my edges here. I'm going to now go back over to surface. I'm going to choose freeform. I'm going to do boundary surfaces. So this is just taking your curves and converting that to a surface. Now I'm going to drag this E value, so my edges from this Delaney edges component into here. Can turn this one off. Let's even turn our forest. Oh, that doesn't look right. Maybe let's try it. I did it earlier, so let's just double check. I guess we do want to do a Delaney mesh. My apologies. So let's go back. Let's get rid of this one. We'll still keep those boundaries, but yes, let's actually do it as a Delaney mesh. So again, mesh, triangulation, Delaney mesh. It's going to create this kind of polygonal look to it. The next thing we want to do is find the mesh or the let's do face boundaries. So I'm going to stay in the mesh area. I'm going to choose analysis. I'm going to do face boundaries. And here you'll see it's really kind of creating the same thing, but for whatever reason, this process or workflow works more effectively. So you have this kind of cool looking geodesic curves. And now I'm going to take these curves. So these boundaries, you can see it's producing curves. So the face B, drag that into your edge boundary. And now you actually have them in just a bunch of different smaller surfaces. I'm going to turn this one off so I just have my surfaces looking here. And I'm going to now flatten this. So I'm going to right click on the S of this output, say flatten. That way it's just all being grouped into one area. And you'll see that you've got quite a bit. It shows mine has just a little over 1,000 trimmed surfaces. Okay, so now we have a lot of variation to our surfaces. Does this all make sense? So now, instead of looking at, in my case, I have 3 little mounds of forest to analyze. Now I have over 1,000 faces to actually analyze to get a more detailed results. Make sense to some degree? Okay, so what I can do now, because I know this is all part of the forest still, I can now find the slope of each one of these surface types, because you'll see in that presentation I showed yesterday or the day before that your coefficients, let's see where it's at. They depend on not only your sand type and your surface type, but also that slope percentage. So like I said, we're going to work with our woodlands, and now we're going to break it down into which ones are considered flat, which ones are considered rolling, and which ones are considered hilly. So that's why we want to get a large range of slope percentages, because you can see it goes from a 0.1 coefficient to a 0.3. It's still pretty small relative to the rest of those coefficient values, but there's still a pretty dramatic difference depending on the slope percentage. It doesn't change a whole lot when it goes from rolling to hilly, but flat definitely has a much lower value. So that's why we want to get a more accurate depiction of our slope percentages. This is where you need to choose what's soil type. I'm just going to stick with a sandy loam. Obviously, you can choose one or these other ones. This is just to kind of keep things simple. Okay, so I know that. So here, again, you divide it. So now we're going to find the slope of all our different surfaces and then break them down to which ones are 5%, 0 to 5%, which ones are 5 to 10%, then which ones are 10 to 30%. You're probably going to have slopes that are above 30%, but that's fine because you can just still classify it as this. So don't worry about having those percentages that will exceed it. Okay, so now we need to determine the slope of each one of these surfaces. We've done that quite a bit in the slope grading class, but I'm assuming you've all completely forgot how to do that, probably. But the good thing is we get to do a little refresher course. I still have to do this every time, and it's kind of annoying, but it is what it is. So I'm going to go back to my surface tab. I can go to analysis, and I'll just start off by saying, let's evaluate these surfaces. The one all the way near the bottom, I see that I'm being asked for a surface, so that's this one, but it's also asking for a UV point. So that's essentially going to find the area or a point within each one of these small triangles and give us a direction it's pointing at for measuring its angle. So in order to do that, we need to find the area of our surfaces. So I'm just going to double click my screen here, type area. This is going to be a critical component as well, because this is giving us an area, which is a variable for our equation. So maybe you want to somehow highlight that. Sometimes if I just want to give it some difference between the rest of those components, I'll just hit Control G to give it a box around it, because I know I'm going to be using that later. I'm then going to use my, still within the analysis section, do surface closest point. I'm looking for the point, so that's all these. And again, it's asking for the surface, that's just right here. And now I have my UV point value. So now I can drag that into here. Now I can see all the different angles in which these surfaces are pointing. I can turn off pretty much these ones. I can even turn this one off. So I'm just still left with my surfaces. Again, this is a quick way to just visually know if your surfaces are pointing in the right direction. I'm going to go over to Curve and do Line SDL. And I'm just going to put these in directly across. And you'll see it gives us these kind of hairs pointing out what the tangent of these surfaces are. So they're pointing in their direction that they're facing. So that's good. I don't know why that keeps popping up, but it does. So we should be all set there. Oh my gosh, let's do... So now we can actually measure the angle or the normal of these versus the relative z vector to find the actual angle of these slopes, so the slope percentage. So now I'm going to take that normal, I'm going to go over to vector, go to the vector tab, and say angle. So this is again measuring between two angles. I have the angle of all my surfaces. Now I need to find that between my z vector to essentially look at what that angle is relative to the vertical direction. So I'm going to double click, hit Z. I'll choose unit Z. So choose that component, drag that into there. And now that's giving me an angle in radians. Unfortunately, this calculator doesn't know how to measure the coefficient of surface types in radians. So we need to convert that to slope percentage. I can do that by going over to Math, my trigonometry section, and do arc tangent. I'm going to plug this value into here. So this is going to convert it into a decimal version of a slope percentage. So we now need to multiply that by 100. So I'm going to drag that into there. Just double click on the screen, do quote 100. Because I know this, the value isn't ever going to change. So now I should have slope percentages of all these different surface types. If I pull out a panel over here, you can see here's all my different values. You can see there's a lot of values, at least for mine, in the 60s. So like I said, these are where you're probably going to have some slopes that exceed that 30%, and that's fine because we can still manipulate that a little bit. So just so we don't have to deal with a lot of these variables being above that 30%, because that's what the calculator uses, I'm just going to cap all those values that exceed 30% to be 30%. There's really it's not completely necessary, it just helps clean things up a little. So I'm going to go over to utility in the math section still. I'm going to select minimum. So this is going to, like it says, return the lesser of two items. So if I drag this into here, and now I write 30, all those values that exceed 30% are just going to get capped at 30. So you can see now all those values that were in the 60s and 50s are now registered as 30, but everything less than that is going to stay as is. So yeah, there's quite a bit of steep slope percentages. So I see a lot of 30s. Okay, so now we've got our surface types, our surface areas, and now they're percentages. Now we're starting to get into the calculator aspect of this. We've kind of set up our analysis of everything. So now, like the calculator shows, we've got them divided into their different slope percentages. Now we just need to separate them into these three categories. So the best way to do that is to run another math operation to separate those. So I'm going to go to math still, go to operations, and let's do smaller than. So choose this one down here. So I'm going to plug this value into smaller than. And we're just going to start off with the lower values and build our way up. So I'm looking for values that are smaller than or equal to 5%. So I'm going to do quote 5, because this is going to separate our flat woodland. So finding out that 0.1 coefficient. So this gives us a pattern that says whether that slope is in fact 5% or less. Now we have to use our dispatch component to actually separate that information. This is just giving us a pattern to build off of. Now we can actually physically separate that information. So I'm going to go over to set, the next tab over, choose list, and select dispatch. This component uses that pattern organization along with your list to separate data. And we're going to need several of these. So I'm going to first create one. We're going to need the area. So that's why I highlighted this. We need the area. So use the A output, not your centroid or that point output. Make sure to select this area or this value. Drag that into our list. So this one. And then I'm going to use the equal to or less than as my pattern definition. And you'll see if I look, there's only 3 values that are less than 3% in the forest area versus all the other remaining values. What I'm going to do now, just to again keep things organized, I'm going to right click this and say surface area. I'm going to copy this and paste it, use the same pattern rule, but now I want to also look at let's do it for my slope percentage. So I'm going to drag the minimum one. So this could be slope percent. I'm changing that minimum component to say slope percent. I'm going to drag that into this list and call this forest slope. I'm going to bring some panels out over here so you can see what the area is of those 3 surface types and also their corresponding slope percent. We aren't going to really need anything. It's just to help organize our data again. This is really the more important one. Okay, so we did it for our 5% slope. Now we have to do it for our 5 to 10% slope and then everything after. So again, I'm going to go to math, do smaller than or equal, but now I'm going to use these remaining B values. So this is, again, looking at the forest slope. That gives me those 3 values, but then it also gives me all those other remaining values. So I'm going to drag that into my A and say now, because I know everything, there's nothing that's less than 5% because those have all been grouped into here. So now I can just do 10. And so now it's going to tell me how many are within that 5 to 10% versus what's greater than. I can take this surface area, again, just going to copy and paste that one. I'm going to use the, again, smaller than or equal to value for my pattern. And for my list, it's still in the right area. I just want to know the area. And so now I have my, let's call this still surface area. I'm going to change A to say, what were they classified as? Like hilly and mountainous, I don't know, rolling and hilly. So let's call A rolling and B hilly. And just for the sake of clarity, we can also do this as flat. And I'm actually, we actually don't want this as our list value. We want this as our list value. So I'm going to drag that into there. And now we should have it nice and organized. So I'm going to just paste these panels here so I can just see what those values are. I at least know that they're all the surface area. Okay, so now we've got our analysis of our forest area all organized. Now we need to actually multiply the area by the coefficient. So we know that the flat has a 0.10 coefficient. These rolling ones have a 0.25 coefficient, and the hilly has a 0.3 coefficient. This is, again, we're trying to, for this equation, if I scroll down here, we're looking for the C average because we can't, again, assume that they all have the same coefficient value. We need to find the average for each one. So we're finding the average of all the forests between those two slope percentages. And then we'll do the C average for our meadow and our lawns. Like I said, this is where it's going to start to get a little repetitive, but it shouldn't be too exhausting. So we have all the area in square feet. Now we have to convert that into acreage, but we want to add them all up together within their designated section. So I'm going to stay within this math tab, choose mass addition. If I want, I can paste this and just see what that total square footage is. I'm just going to copy and paste that down to these. So now I have my total area, again, in square feet, but we need to still find the acreage of each one of these. So I'm going to now divide these values by 1 acre, which who remembers what square footage of an acre is? Oh, man.
43,000 and some change.
43,000 and some change.
What's that symbol? Too small to see.
I'm just asking for what the value or the square footage of an acre.
Quotation 43?
Well,
43560.
560, good. Hopefully before you guys graduate, you've memorized the square footage of an acre.
43560.
Yep. Okay, so this is giving our acreage of each one of these areas. So I'm just gonna copy and paste this down to each one of these. I know I've got probably too many panels up, but that's fine. You can see what these values are.
Can you pause for just a second, verify that, yeah, because a lot has just happened. I'd like to just make sure that these last couple of things.
Well, we have this being recorded, so I don't really
You
want
can't
to.
pause?
No, it's going to mess things up.
Then I'm done.
That's why we were recording, so you can always refer back to it.
All right. That sucks.
Okay, so we have our total acreage. In order to find the C average, we multiply the acreage of that type by its coefficient. So this is where we're going to finally multiply it by those C values. So I'm going to take my acreage, multiply this one by 0.10. I'm going to multiply this one by 0.25. And then multiply this one by 0.30. Now we finally have that C average for each one of these coefficients. Now, once we've done that, let's go ahead and add all of these values together. So this is going to be like the big one. We're connecting a lot of information. So I'm going to, again, highlight this. And again, we're just using the mass addition one. So I'm going to add this one, and add this one. Okay, so now this is everything for our forest surface type. So like I said, it takes a little bit of work to get there, but now here's the easy part. We can literally just take this whole part of our component. Don't worry, it's okay. Everything before we add it all together, we're going to take it all. We're going to simply copy and paste it. And what do you think we do with that?
Do the same thing, we're just going to change it to at the beginning so that it's the other.
Yeah.
What is it, the pastures?
Yeah, let's do it. Let's actually copy this one too. That way we don't have to plug everything into there. So we're literally copying this entire script, everything we've done. And what was that we do again? Just substitute that surface?
Yep.
Awesome. So let's go ahead and turn on our pastures. So I think I have mine messed up. Let's do it. I think this is technically that classification. So that's cool. It's just actually one surface even, which is nice. So I'm going to right click on this to change it to say pastures or meadows. I can never even remember these surface types. Oops, I think it's higher. Pastures, yeah. So pastures, set one surface. Well, that's pretty gnarly. So I might want to give it a couple, like do it a little bit more intense in terms of the number of points for this one. Let's try like 500. Oh geez, I don't like that at all. So I might not just like having this single surface. That's too bad. I'm actually going to split that then because I can see that it clearly does not like it. So I'm going to go to Rhino real quick. So this is a good thing is to learn, okay, maybe I need to at least separate it into multiple surfaces. I don't necessarily have to change the amount, but I am going to use that nifty tool I showed you guys last week where I interpolate on a surface. I'm just going to draw here. I'm going to say split this curve Try doing another one over here. Oops. Split. Yeah, and I might have just done a terrible job in deciding how I want to draw this, but oh well. So, okay, so now let's try having multiple surfaces. So I'm going to go back here, say set multiple surfaces, and see if it likes that a little better. That's a little better. Still not a huge fan because of all those weird parts, but okay. So word to the wise, don't get too crazy with your surface divisions. Okay, so let's keep moving forward. Again, it's kind of a little messy, but that's okay. Okay, so now we have our pasture surface types. The only thing we have to do with these is actually change our coefficient values. So if you go over to these ones, so I have 0.1, 0.25, and 0.3. I'm going to change those to now. So now I'm in my pasture lawns. So the 0.10 can stay the same. That's still flat. Rolling is 0.16, and then hilly is 0.22. So let's do, oops, 0.16 and 0.22. Perfect. So that's those values. And what do I have to do now?
Copy it again.
Yeah, let's just keep copying. And now I'm just going to now do it for the other ones, which are going to considered, let's call it no surface cover. So again, it's probably going to be a little messy, but oh well. Set multiple surfaces. Oh, that one actually doesn't look too bad. I'm going to say no plant cover. It's essentially just exposed dirt. It actually looks pretty good. It's not too much overlap. The good thing about this is even though there's technically more surface that's being modeled than there actually is, it's always good when it comes to stormwater runoff to overcompensate than to underestimate the runoff volume, because you do that and you flood areas and have to pay for property damage and all that bad stuff. These are also a lot of assumptions, and it's simulations, so they aren't intended to be precise, just accurate. Again, there's that fun word of precise being versus accurate. Okay, so the last thing we have to do is what?
Change the coefficient.
Change the coefficient. So again, I'm going to stick with my sandy loam for cultivate no plant. We can see these go up quite a bit. So I have 0.3, 0.4, 0.52. Should at least be easy to remember. 0.30, 0.40, and 0.52. Okay. Yay, so now I have my coefficients for these. And now that I have that, this is again just finding the C average, the coefficient average. You can see once I do that part, so I've multiplied my areas by their coefficients for all those different surface types, going to divide it by the total acreage of my site. So this is again why it's good to have that single solid surface, which you'll use for all those other equations. Let's go ahead and add all these values up. So I have these 3 endpoints that I need to mass addition for. So I'm going to drag that into there, move it down, do it for here. So again, we're adding all these values using the mass addition. Now I'm going to add this one. So I have my average C per acreage. Now I'm going to divide that by my total surface area and acreage. So I've got my single surface selected out here. I'm going to reference that as well. Set one surface, find the area. Again, this is in square feet, so I need to convert it to acres. Let's divide that by, who remembers what an acre is?
43,560.
Yay. Which gives me, so it's about 40 acres. So this value is now going to be divided. So I have my total mass. So A divided by this. And I have an average coefficient of 0.6. Okay, I'll buy that. Should actually be, it's probably because of all that overlap, but oh well. And the majority of it's kind of flat in those areas. But. Okay, or no, it's mostly steep, that's why. Okay, so now we finally have our C average. Now what do we do? Not quite.
Divide by 8.2.
No, that's what this equation's. So we found C.
Oh, so gotta apply IA. We already know
Yeah.
that.
So I guess that's kind of weird that you multiply and divide, but oh well. Okay, so what is that? So what is I?
Intensity of rain.
Okay, what's the intensity for the assignment?
I don't know.
It's in the assignment. So we're looking for inches per hour.
Oh, that wasn't me.
Well, yeah. Is it?
It's on the second page of the assignment. I'll give you as a hint. What information does it say
1
about
hour
them?
long, 2-year storm event, 1 inch of precipitation.
Okay, so what's that intensity mean then? So I'm looking for inches per hour.
1 inch per hour.
So how long is the rain event?
1 hour long.
1 hour long? How much rain?
2-year storm event, or 1 inch. So 1 inch.
1 inch per hour. So simple 1 IPH. If I multiply this value by 1, it's going to be the same, right? So I can technically just leave that value out.
Ah, I see what you did there.
Yeah. So now I'm going to multiply that by what? So I've got intensity, which is 1, which is the same. I mean, I can technically change that to 1 in case I want to change my IPH. So I'm going to do 0.5 less than 3. I'll just change it to 1. That way, if I want to be an overachiever and see what the runoff volume is for other intense rainfall events, I can do that. Little tip for you. So now what do I multiply? I've got my C average.
You gotta multiply by the total area of the site.
Yeah, which is, we've already done that, right? So we divided that by acres, so 40 acres. So now I'm going to multiply this value by my acreage. So I've got my overall surface, found the area, divided that by 43,560. So I'll say this is total surface area. Multiply that. And now I've got, wow, that's pretty intense. Now I've got a peak flow runoff of 24.6. That's really fast.
Cubic feet?
So yeah, 24.6 cubic feet per second. It's pretty devastating, right? I'd buy that with this kind of steep condition, even with those steep places planted with forest, they can only do so much to reduce that peak flow runoff.
It's a lot,
It is a lot.
especially for a 1 inch.
Well, it lasts for an hour too, so. Okay, so now what?
No, we don't.
Nope. We have to, this is just peak flow runoff, right?
Yeah.
This is cubic feet per second. What am I asking for in the assignment? So if we're looking for, if I've got flow rate,
Stormwater. Any total at the end?
total of what?
Total amount of runoff?
Runoff what?
Volume.
Volume. Remember, volume versus rate, completely different things. If you were to say 24.6 cubic feet of runoff volume, I'd say try again, because that's clearly not going to be right. I guess. So, no, that's runoff rate or peak flow rate. So, how do we find the volume again? I have 24.6 cubic feet per second. I just need to know cubic feet.
So you multiply that times however many seconds there is in an hour.
Yeah, so how long is the rain event again?
1 hour.
So how many seconds is that?
That's 60 times 60. 3,600.
3,600, woohoo. So let's multiply that value by 3,600. We multiply that together. And now we've got our runoff volume. So mine's about almost 90,000 cubic feet of runoff. Sounds about right.
And how many acres?
40? Yeah.
Cool.
It's not outrageous, that's for sure. So yeah, now you get to have your little squid-like script for this. So, like I said, for next week, you need to find a way to show this amount of runoff, whatever yours calculates. There's obviously all sorts of different ways you can do that. You could try and find like the lowest point of the surface. So we've got, what, 7 minutes? Let's brainstorm.
Yeah.
I'm gonna just turn off everything here. So how could I do that?
Photoshop.
No.
You want to graphically show it.
Yeah, how do I graphically show? Like this is the whole value of having runoff calculator and 3D modeling. Hence 3D modeling.
What if you, I want to start with some sort of shape. Like, let's just say I started with a sphere.
Okay.
And what the volume of that sphere.
Great example. No, we aren't going to use kangaroo for this. You guys can hardly keep up with those. So. Okay. So maybe for this, I'll try and find the lowest point. So for this, I can take my surface. I can look at all the points of this surface. Let's not do it that way. Let's make some assumptions. Let's just say the water's all flowing over here. So I have my point. So I just made a point in Rhino. I'm going to reference that as my base plane. Oops, let's just use a point to reference in there. Okay. And so now it's asking for the radius. Again, I have no idea off the top of my head the corresponding radius of a sphere to its volume. So I'm going to go ahead and type volume first. Look at what the volume actually is for this. And see that it is 40 or 4 cubic feet. Quite a bit off. So let's make a gigantic slider, like, I don't know, 50 less than 500. Oh, that's way too much. Okay, so let's try 25. Okay, 65,000. Now we're getting there.
Are you trying to make it match?
Yeah, because that's the volume. So 73,000. I have 88,000. So let's try 28. Nope, too much. That's where you just kind of have to finesse it. Oh, that's getting close. Let's add some decimals to this. Max will be. Do you have any other numbers? 28.76, anyone? Okay. 89 up. You went over, you're out. Any other number? Price is wrong.
27.63?
No, you already answered, you're out.
Alex.
I'll try.
What do you say? And the answer is 88,355. Oh, I'll accept that. So yeah, now you can see how much runoff volume is being generated from the site. Overall, not that much. It sounds like a lot. So this goes back to that whole conversation of relativity, right? Like 88,000 cubic feet sounds quite a lot compared to a 40-acre site. Not that much.
So that site is producing the same amount as that sphere?
Yeah.
Oh, that's not a lot.
It's not, right? Makes sense. It's all natural landscape. See, now you see the value of preserving natural landscape and how little runoff is being produced. Kind of goes back to that conversation we had in the very beginning where generally high functioning, healthy landscapes only have about 3% of runoff volume. That's probably pretty close to 3%.
Okay.
Now, here's the crazy part. What if you were to change, this is what we'll get into later in the semester, dealing with urban environments. What happens if, let's say we're going to cap off all of that flat no cover area and change that to being asphalt?
Oh.
Yeah, because we want to have or we want places to park our cars, right? So we can go and hike the mountains. That seems responsible.
Yeah.
So let's see what that C value is. So asphalt on concrete. Let's go big with 0.95. So I'm just going to plug 0.95 into all three of these and just watch this volume grow.
Just watch it flood.
If I was good about it, I would have found a way to have a responsive with the volume. So now we're talking 141,000. No, that's not too much.
All right, let's put more asphalt in.
Yeah, let's just get rid of those trees. We don't need them.
Then again, if you're in an arid environment and you want to capture that water, you might purposely put some asphalt down.
No, you probably shouldn't. No,
No, don't do that.
because then you're interfering with the overall ecology of everything.
That's it. You open up a can of worms.
Oh,
Not
we
that
can put a whole
much.
bunch of roads in there then. Let's do it.
Yeah, let's keep doing it. Who cares about habitat and refilling our aquifers? Yeah, screw them.
You're going on.
Yeah. It is right, yeah.
You're up, but no.
Yeah, I don't think it's going to make that much of a difference. But anyways, so find ways to accurately represent the runoff volume. Maybe you want to give multiple scenarios. So maybe instead of it being 1 inch, what happens if it's 3 or something? 3 inches per hour, and that's probably what a monsoon is. Now we're talking about almost 500,000 cubic feet.
Well, for perspective,
It's too high.
I'd like to see a 6-foot tall line to see how big is a person relative to that line.
Okay.
That'll tell us how big of an engineering feat it
You
is
ain't even gonna see it.
to capture that.
Yeah.
Yeah, it was up there.
That's a lot of water. Next to a mountain, it looks like a lot of water.
Yeah, there's your person.
So 4, 6, 3.5 million gallons.
Yeah. So yeah, there you go. Have fun with it. So let's think of it this way. What if you guys should probably have a drainage script, right?
We probably should.
Maybe at the end of each one of those drainage curves, you showed the average runoff volume from that. So if you were to divide however many curves you have, divide the volume by that, that gives you what each individual curve produces. That's obviously not a complete direct relation, but something. So yeah, be prepared to show those on Tuesday.
You gotta show them the curve.
Yep.